So problem 2.8, we have two lines inside, each containing 10 oscillators. So we have the NA, which is the number oscillator of A is equals to 10, and NB is equals to 10 as well. Total number of energy is equals to 20. So what is the total number of oscillators? Well, it's going to be simply equals to the summation of NA and NB, which is equal to 20. So how many number of macrostates are there? The number of macrostates is simply going to be equals to the number of energies plus 1, which is equals to 21, because of 20 plus 1 we said. So part B, how many microstates are related to the system? So total, which just means we have to calculate 20 and 20 for N and Q. So we're going to have 20 plus 20 minus 1 factorial divided by 20 factorials, and times would be 20 minus 1 factorial, which will be 19. I'm just going to write 19. So here we have 39 factorial on top divided by 20 factorials times 19. Okay. So we have 6.89 times 10 to the power of 10 in total. Now for C, we have a similar system is in thermal equilibrium with the probability of finding all the energies in solid A. So we have that the microstates for solid A are going to be equals to, well, 10 oscillators, 20 units of energies, which is equals to 10 plus 20 minus 1 divided by 20 and then 9. Okay. This is equals to 39 factorial divided by 20 factorial times 9 factorial, which is equals to, I'm just going to round it up, 1 times 10 to the power of 7. Okay, but now to find the probability, we know the probability is equals to the multiplicity of A times the multiplicity of B. So we have to find the multiplicity of B. So we know it's 0, comma, sorry, it's 10 oscillators, 0 energies. Okay, so we have, oops, I'm getting rid of this already. Okay, yes, 10 plus 0 minus 1 factorial divided by, we're going to have 0 factorials times 10 minus 1 factorial. So we have 19 factorial divided by this one is going to be equals to 1. So we're just going to skip it. 9 factorial. Sorry, here we have 9 factorial on top, so we just get 1. So, sorry, this is the multiplicity total. I don't know what I'm saying. Okay, so multiplicity total is equals to this first one. I'm just going to write here for a moment. We'll see why. Times 1. And the problem on the other. Okay, so it just equals to this. Reappear over here. So the number of probabilities is equals to 1 times 10 to the power of 7 divided by the total number of multiplicities, which is equals to this part right here. So we have 1 times 10 to the power of 7 divided by 6.89 times 10 to the power of 10. So it's equals to 1.45 times 10 to the power of negative 4. Now, of course, you multiply by 100 and get a percentage. Now instead, what is the probability of finding exactly half the energy inside A? Well, we're going to have that multiplicity of A, it's going to be equal to the multiplicity of B actually, because we have the same number of oscillators, so we're going to have the same number of energies that will be thermal equilibrium. So this is equals to, for 10 and 10. Okay, so this is equals to 10 plus 10 minus 1 factorial divided by 10 factorials times 10 minus 1 factorial, which is equals to 19 factorial divided by 10 factorial plus 9 factorial. Okay. this is equals to 9, 2, 3, 7, 8. Okay, but again, we know that we have to find the total. We have to take the first one, A, multiplied by B. We know it's the same, so we're just going to have 9, 2, 3, 7, 8 squared, which is equals to, let me put it in scientific mode, 8.53 times 10 to the power of 9. Okay, so probability will be equals to 8.53 times 10 to the power of 9 divided by the total number of multiplicity, which is equals to this part right here, 6.9 times 10 to the power of 10. So we get 1.23 times 10 to the power of negative 1, which is about 12%. Okay. Then what would find exactly half the energy inside A? Am I doing part B? Yes, okay. I feel like I've just done this. Oh yeah, I just done D. Yeah, exactly. E. I skipped C. No, I've done it. No. Where? Okay. So E. On the work will the system exhibit reversible behavior? Well, this is not math. We would see reversible behavior whenever we see that the energies are split between two of them equally, in this case, because we have the same number of oscillator. And we know, for example, let me just write. So here is a multiplicity, and here is our Q for A, for example. And now we have 10, which is the equilibrium. So we have something like this. So whenever our system enters this part right here, it will be irreversible. We'll never see our system going back to these energies right here, as it will actually require work for that to happen. So an irreversible behavior would be when we have all our energies, we have our energy split between two solids, and it's so unlikely that it's considered irreversible.